Okay, welcome everyone. Great to see this turnout on this day, which is the last day of CDAC Webinar Talks, final for 2020. I'm very pleased to introduce Tianga B. from the Department of Chemistry, University at Buffalo. We like to claim Tianga as one of our own in the sense that she was supported by CDAC as a grad student at Buffalo starting around 2015, where she worked with CDAC partner Eva Zurich, and she's now a postdoc with Eva. Before completing her PhD, she conducted a broad range of computational studies of materials under pressure, including high TC hydrides and other novel materials, and she got her PhD earlier this year. And that work led to a lot of highly cited papers, including a number of beautiful reviews that are well recognized in the literature. And she continues to be a part of the CDAC investigations of high temperature superconductivity. We're very pleased you were able to give this talk, Tianga. Please proceed.
Right. Thank you so much, Professor Henley. Can everybody hear me well?
Just fine.
Okay. So hello, everyone. I will give a presentation today on my PhD work for 4 different hydrides under pressure. So first, I would like to give a little bit introduction. Chemistry under pressure can be very different from our chemical intuition at the ambient conditions. The pressure variable can be used to access new materials with novel stoichiometries, novel electronic, structural, mechanical, and magnetic properties. For example, I show 2 structures here. These 2 cage-like structures are lanthanum decahydride and trihydrogen sulfide. These 2 structures were predicted and synthesized under pressure, both with record-breaking high superconducting critical temperature TC. However, not all of the high-pressure hydrides would have TCs. For example, iron H5 showing here was also synthesized under pressure with bulk atomic hydrogen, but there was no superconductivity was found. So why focus on hydrogen-rich materials? In 1935, Wigner and Huntington predicted that hydrogen can become alkali metal-like monoatomic solid above 25 GPa. However, later studies suggest that the metallization pressure is much higher than that. In 1968, Ashcroft proposed that this solid hydrogen could become superconducting with a high TC value, potentially higher than the room temperature. However, the superconducting transition temperature have not been accessed in experiments yet. So later he made another proposal for a new idea that introducing additional element might bring down the required pressures through chemical precompression. Therefore, we study the hydrogen-rich materials under pressure, trying to find novel superconductors and estimate their TCs using either the Allen-Dynes modified Macmillan equation showing here, or numerically solving the Eliashberg formalism. So next, I want to briefly go through the computational methods we use in our projects. So to explore the phase diagrams, we sample the potential energy surface using crystal structure prediction method. And the code we use is named as XtalOpt. This code is developed in our lab based on evolutionary algorithm. So I show an example view here. In each run, we would input the chemical composition. The newer version of XtalOpt also allows us to input space group and define a range of formula unit for each run. Then XtalOpt will generate random structures as the first generation based on the criteria we put in as input. And these structures will be optimized using density functional theory implemented in the Vienna ab initio simulation package. And after optimization, XtalOpt will apply fitness function based on enthalpy to evaluate these structures and to select the parental structures. The offspring structures are generated by applying mutation and breeding operators on the selected parental structures, and then the whole procedure loops back to the optimization step. Ideally, we will find the global minimum structure after many generations. So this page listed the operators used in XtalOpt, including crossover, strain, exchange, and ripple. The combination of strain and exchange creates permustrain, and ripple is strain plus ripple. So this flow chart is an overview for the procedure we use in our computational works. For example, we start from the crystal structure prediction to explore the potential energy surface using XtalOpt for certain stoichiometry at a chosen pressure. Once we get a collection of the global minima structures for several stoichiometries, we would plot the enthalpy of formation against the hydrogen content to construct the two-dimensional convex hull. Any structure that's located on the hull are considered thermodynamically stable. And for the dynamic stability, we use either phonopy or quantum espresso package to calculate the phonon spectrum. For the thermodynamically and dynamically stable structures, we will analyze their structural and electronic properties. And for the promising metal structures, we will also calculate their electron-phonon coupling parameters using quantum espresso package and estimate their TCs using either the Allen-Dynes modified Macmillan equation showing earlier, or for the systems with large lambda, we would also calculate the Eliasberg TC. So the first system I studied was phosphorus hydride. We actually carried out 2 studies on this system. And the first part I want to cover is in the pressure range between 100 and 200 GPa. This work was published in 2016. So as I mentioned earlier, that trihydrogen sulfide was found to be a high TC superconductor. That motivated the works on another of the hydride system on another p-block element, phosphor. So in 2015, Drostov and co-workers observed a TC of 103 Kelvin at 207 GPa after loading phosphine into the diamond anvil cell. The lack of structural information from the experimental paper encouraged us to carry out our computational study on this system, and we were among the earliest to publish the results. The following papers came out around the same time. So initially, we started our project on the classical stoichiometry of PH₃, and we found that the global minima structure of PH₃ is unstable with respect to decomposing into phosphor and hydrogen. Therefore, we expanded our search to pH from pH to pH₃. And in fact, all of these structures are thermodynamically unstable. However, at 100 GPa, the formation of pH₃ requires the least energy, and at 150 and 200 GPa, pH₂ is the most stable stoichiometry. In addition, the formation of pH₃ from pH₃ and hydrogen, and the decomposition of pH₃ into pH₂ and hydrogen are both exothermic. And also at 200 GPa, which is the most important pressure for us, pH 5 is more stable than pH 2 is more stable than pH 5, and therefore we focus our analysis on the stoichiometry of pH 2. So from our evolutionary research, we identified three dynamically stable pH 2 phases, including 5 formula unit C2M phase, 2 formula unit C2M phase, and an I4 triple M phase. More importantly, the formation of pH 4 to 6 from pH 2 and hydrogen at all pressures, and the decomposition of pH 2 into pH and hydrogen at 150 and 200 GPa are both endothermic. So for the three pH 2 phases, below 153 GPa, the 5 formula unit C2M structure is the most stable one, excluding 0-point energy. Above 153 GPa, the 2 formula unit C2M and I4 triple M becomes preferred. So at 100 GPa, the most stable structure is the 5 formula unit C2M. This structure is comprised of oligomers, and the structure of it is showing here. The oligomers extend along the C direction, and it's one-dimensional periodic along the A direction. The phosphor atoms within the pH and pH 2 segments of the oligomers form square net, which is not uncommon. It has been seen in the simple cubic phosphorus, which is the stable phosphor phase in the pressure range from 11.1 to 137 GPa. And this structure is metallic at 100 GPa, and it is nearly free electron-like. So at higher pressures, the 2 formula units C2M and I4 triple M phases becomes preferred. These two structures are actually structurally related. They both have the phosphor atoms. The phosphor atoms are octahedrally coordinated, with 4 other phosphor atoms filling the equatorial position and 2 hydrogen atoms filling the axial position. The major difference between these two structures is that the I4 triple M structure is the bond angle in it is perfectly octahedral, but in the 2 formula unit C2M, the hydrogen is canting with an angle along the line that's perpendicular to the phosphor square networks. So the canting angle at the 100 GPa is very small, so these two structures are nearly identical. But at 160 and 200 GPa, as the plot showing here, the canting angle increased to 9.8 and 10.1 degrees. Although the pH bond distance within I4 triple M is shorter, the canting of hydrogen in the C2M phase results in a more efficient packing and therefore smaller volume for the C2M at higher pressures. So the smaller volume of C2M also result in a smaller PV contribution to the enthalpy. However, because the electronic contribution favors the I4 triple M structure, the I4 triple M structure is preferred by a few millieV per atoms. But at the 200 GPa, these two structures become almost isothermic. So both of the structures are metallic, similar to that of the 100 GPa 5 formula unit C2M. They are all nearly free electron-like. So for both of the structures, their density of states at the Fermi level are mainly originated from the phosphor P characters and hydrogen S characters, and it's indicative of hybridization. We wonder if there's a low energy pathway on the potential energy surface connecting these two structures. Therefore, we we used the notched elastic band calculation to create the pathway, and the calculated barrier was 270 milliev per atom, suggesting that these two structures lie in different wells on the potential energy surface. So then we calculated the electron phonon coupling parameters for them and estimate the TCs. So we would expect at 150 GPa and below, the two formula unit C2M and I4MMM phase would have the similar TC value due to the similarity in their structures. At 200 GPa, the I4MMM have a slightly bigger lambda, but smaller omega log. The larger omega log in the two formula unit C2M phase could be because of the fact that the canting angle result in a larger number of hydrogen that can be found within 2 angstroms away from one hydrogen atom. And that increased the frequency of the related moles. So for the lambda, the major contribution was from the phosphor hydrogen interactions and hydrogen-hydrogen interactions shown in white here. The phosphor-phosphor interactions also contribute, but it's not as much. So the estimated TC values is smaller than the largest measured experimental value. However, our data matches the another round in the experiments, which is colored in orange here. Also, it could be a result of the fact that the experimental measurement was taken on a mixture of metastable phases. So as a conclusion, the classical stoichiometry of pH3 at higher pressure is thermodynamically unstable with respect to the decomposition into the elemental phases or pH2 and hydrogen. There are other reactions may occur under pressure, including the formation of pH5 and pH2 decomposing into pH and hydrogen. We identified 3 dynamically stable pH2 phases that we discussed in this section. And we found that the 2 pH2 structures with the calculated TC as 76 and 70 at 200 GPa would be the good candidate for the measured superconductivity. So we have another study that's also on the phosphor hydride system, but focused on a lower pressure region. So this study was completed and published in 2017. So in this work was based on the fact that in the same experiment, researchers measured the TC around 30 Kelvin at 80 GPa. Although there are many papers already studied this system under pressure, the lower pressure phase diagram was not carefully investigated. Therefore, we decided to carry out this study to analyze the lower pressure structures. So we carried out our evolutionary searches at 40, 60, 80, and 100 GPa. And similar to the previous project, we studied the stoichiometries of pH to pH6, and they are all metastable. So their enthalpy of formations fall into the range of 15 to 55 milliev per atoms. Because there was no phase transitions for pH 1 to 4 and 6 below 100 GPa, and the experimental measurement was taken at 83 GPa, we decided to focus on the results we got at 80 GPa. So first, I want to discuss pH 5, which is the most stable stoichiometry. So this structure is comprised of molecular building blocks. as P2H10 as the molecule showing here, which resembles the 3 center 2 electron bonds in the diboron molecules. So 2 out of 5 of the valence electrons from phosphor would form 2 center 2 electron bonds with the terminal hydrogen, and the rest would form the P2H2 ring here, which is 3 center 2 electron. And the gas phase optimization confirms that the pH bridging bond is longer than the pH terminal bonds. So in the molecular orbital diagram showing here, HOMO -4 to HOMO -9 of the building block resembles HOMO to HOMO -5 of diboron, and HOMO to HOMO -3 of the building block have the same nodal plane as the unoccupied molecular orbitals of diboron showing here. But unfortunately, this structure is non-metallic, so it's not the candidate for the superconductivity. So for pH 1 to 4 and 6, the structures are all comprised of simple cubic-like phosphor layers capped with atomic with the top and bottom layers capped with the atomic hydrogens and separated by the molecular hydrogen layers. Because the pH2 stoichiometry has the physics that with the estimated TC that's in line with the experiment, and the reaction of pH decomposing into pH2 and phosphor, and pH3 decomposing into pH2 and hydrogen are both exothermic. We use pH2 physics for analysis to represent all of the similar structures. So these two physics are structurally related again. The major difference is the orientation of molecular orbitals, molecular hydrogens, sorry. And also in the C2M phase, the pH bond is slightly tilted, and resulting in, again, more efficient packing and smaller PV contribution to the enthalpy. However, because the electronic contribution favors the C-triple-M structure, these two structures are almost isothalpic. At 80 GPa, both of the structures are metallic and almost free electron-like. So we use the notched elastic band calculation to estimate the barrier for the reaction pathway connecting the two pH2 phases. And we get the barrier of 3.1 millivie per atom. We also calculate the barrier for the pathways of rotating all the molecular hydrogen layers, only the side layers and the middle layers in the C2M pH2 phase. The estimated barriers are all considered low, and therefore we conclude that the molecular hydrogens are freely rotating, and this property resembles that in the HCP phase 1 hydrogen. To better understand the mobility of the molecular hydrogens, we carried out molecular dynamics simulations at finite temperatures, and we observed the proton exchange between the molecular hydrogens and the pH units, which resembles that of the phase 4 hydrogen. And at finite temperature, it can form one-dimensional extended and flowing hydrogenate network, but this breaks at 0 Kelvin. So to better understand the role of the molecular hydrogens, we created a set of structures by varying the number of molecular hydrogens from the pH2 phase, and then plotted their enthalpy of formations against the number of H2 layers. Let's take a closer look at this plot. If we compare the two structures of P2H constructed by removing all of the hydrogen molecular hydrogen layers, we find that if we put the pH bond pointing directly at each other, the structure is significantly destabilized due to the increased volume and the Coulomb repulsion between the atomic hydrogens. And if we compare the two structures for pH, we find that if we insert the molecular hydrogens directly in between of the pH bonds, the increased volume also destabilize the structure. We also tried adding extra layers into the PH2 phase and found that the new structure P2H5 has the similar enthalpy of formation as the original PH2. So we believe that the role of the molecular hydrogen layers was to reduce the Coulomb repulsion between the negatively charged atomic hydrogens that's attached to phosphorus. And the stacking fashion of the layer is important. So finally, we estimate the TC values for the stable structures. The two PH2 structures give similar TC values, and their electron-phonon coupling was mainly originated from the phosphor-phosphor and phosphor-hydrogen interactions. The hydrogen-hydrogen interaction region contributes minor. So this is very different from the high-pressure PH2 phase, which doesn't contain the molecular hydrogens. So PH4 have the similar structure, has the lowest TC. This is because this structure, the phosphor layers in the phosphor blocks in the PH4 structures are only 2 atomic thick, and that significantly reduced the phosphor-phosphor interaction contribution. For the pH structure, its TC is also lower, and its electron-phonon coupling is also mainly from phosphor-phosphor and phosphor-hydrogen contribution, but the phosphor-hydrogen high-frequency stretching mode was not included here. Therefore, we believe there's an optimal phosphor to hydrogen to H2 layer ratio that can achieve the highest TC. So to sum this up, we found a high pressure pH5 phase that has building blocks resembles the 3-center 2-electron bonds. We find the structures containing molecular hydrogen layers. They are freely rotating. They can form extended hydrogenic network at finite temperature, and their role was to reduce the Coulomb repulsions. So for all the structures with TC, the electron-phonon couplings are mainly originated from the hydrogen-capped phosphor layers, not the H2 layers. So then I will just quickly move on to the next system of iron hydride under high pressure. And this work was published in 2018. So the chemical composition of iron hydride and its structures has long been the interest of geoscientists. And in 2017, iron H5 was successfully synthesized with bulk atomic hydrogen. Theoretical studies predicted that a TC of about 50 Kelvin and a TC of 43 Kelvin at 150 GPa for iron H5 and iron H6. However, this wasn't observed in the experiment, and another later theoretical study disagreed. So this discrepancy motivated us to carry out our own search for iron H5 to 8 in the pressure range between 150 and 300 GPa. So here it shows the convex hull at the three different pressures. So at all the pressures, iron H5 are located on the hull, and iron H6 is on the hull at 300 GPa and within 9 millieV per atoms above the hull at lower pressures. For iron H7 and 8, the structures are within 10 millieVs above the hull at 300 GPa, but further away from the hull at lower pressures. So although they are not, several phases are not on the hull, we believe the distance to the hull is relatively small, and because they are dynamically stable, so we analyze all of these structures. So first, let's look at this, if there's any superconductivity in the iron H5 structure. From our search, we identified the known F4MMM iron H5 phase at 150 and 200 GPa. And at 300 GPa, we found a new structure, CMCA, that's structurally related to the I4MMM phase. So in both of the structures, they are comprised of simple cubic-like iron H3 blocks. Iron H3 was also synthesized. And these layers are separated by atomic hydrogen layers, and the projection of the atomic hydrogen layers are showing here. So the major difference between these two structures is that in the I4MMM, the HHH bond angle in the projection wheel is either 90 or 180 degrees. But in CMCA, the network is distorted, and therefore giving it a smaller volume and smaller PV contribution to the enthalpy. The hydrogen network in the I4MMM phase resembles the CMCA hydrogen phase, which has the estimated TC of 242 K at 450 GPa. And therefore, we calculated the electron-phonon coupling parameters and estimated TC for these two phases. So we found that if we choose a properly small Gaussian broadening when which is used for the approximation for the double delta function, there's no superconductivity. So that's our conclusion for that part. Moving on to iron H6, we found three structures. We found the known structure CMMM that's stable below 100 GPa, and we found a new structure PMMA that's stable up to 180 GPa, and we found another P2C phase that's stable up to 200 GPa. So all of these structures, again, are comprised of the cubic-like iron H3 layers, but separated by not only atomic hydrogens, but also molecular hydrogen layers. So the difference between these three phases is that in the CMMM structure, the projected view looks like almost squares, and the molecular hydrogens are parallel to each other. In the projection view of PMMA, the atomic layers are slightly distorted, and every second molecular hydrogen is rotated 90 degrees along the A direction. For the P2C structure, the atomic hydrogen layers are further distorted, and now in the projected view, there's the neighboring layers are no longer on top of each other. So at higher pressures, the distorted phases are preferred. So for iron H7, we found a C2C structure stable up to 190 GPa. It is very similar to iron H6 that's comprised of iron H3 layers and separated by atomic and molecular hydrogen layers. At higher pressure region, up to 300 GPa, we found a P1 iron H7 phase that looks different, but actually similar to the known iron H6 structure that's above 200 GPa. It is comprised of iron three-dimensional networks that's extending along the C direction. The difference between this iron H7 and the non-iron H6 is that the channel shape is different, and it contains H3 minus like units showing here. This structure, however, is non-metallic at 200 GPa and 300 GPa. So for iron H8, we found the PMMA structure being stable up to 290 GPa. This structure is interesting because it is comprised of the layers with iron zigzag chains and atomic hydrogens. This layer can be constructed by removing atoms from the iron H3 layers. And then the zigzag layers is separated by atomic hydrogen layers. So at higher pressure, it transforms to an IMA2 structure, which is also comprised of the zigzag layers that, but in the AB stacking. And the atomic hydrogen layers forms a unique X motif. So in this study, we found no superconductivity for RH5, and we identified 3 new phases, including RH5 and RH6. We found 1 more non-metallic phase, P1 RH7, and we found 2 metastable RH8 phases, both with modified RH3 motifs. So the next system I want to talk about is a ternary system, which is methane intercalated trihydrogen hydride perovskite. This project was published earlier this year. So by now, most of the high pressure phase diagrams of hydrides have been, binary hydrides have been investigated, providing the ground for us to expand our searches for the more complicated ternary systems. So this additional element degree of freedom has led to the discovery of some interesting structures. For example, lithium magnesium hydride was predicted to be hot superconductor at 250 GPa. And another example would be calcium yttrium hydride with the also with the glyceride-like hydrogen cage motif. And its TC was estimated to be approaching room temperature at 200 GPa. And comparing to phosphor hydride, the lithium phosphor hydrogen system has a much higher TC at the 200 GPa. So another factor is that there are interesting carbon-containing superconductors. Dense carbides have been predicted to be superconducting, and it's very stable due to its sp3 framework. There were hydrocarbons studied to be stable at high pressures. Also, the ternary systems made by doping methane with either magnesium or potassium were found to be superconducting. Combining these factors with the fact that the trihydrogen sulfide was predicted to be high TC superconductor, we were encouraged to carry out our study on the CSH systems with the stoichiometries showing here. So among all of the stoichiometries, CSH7 stand out to be particularly stable with respect to decomposing into the elemental phases. Although it's not, it does not locate on the Hall due to the fact that it's unstable with respect to decomposing into methane and trihydrogen sulfide. However, first, these structures are dynamically stable. Second, they are close to the Hall. For example, at 130 GPa, these structures were about 30 millieV per atom above the Hall. And therefore, we decided to focus our study on this stoichiometry. So when there's only one formula unit in the cell, we found CM and R3M structure. CM is stable between 100 to 110 GPa, and above that, it transforms to R3M. So the CM structure can be viewed as methane molecule intercalated in between the layers of H5 and H5S. And the R3M structure can be viewed as the H5 sulfur layers are connected by hydrogen atoms, but it can also be viewed as the removing the one of the H3 sulfur unit from the trihydrogen sulfide phase and put in a methane molecule. So we plotted the pressure volume equation of state of the R3M CSH7, and as a comparison, we also plotted the equation of state for its assemblages. So the equation of state for CSH7 lie in between of the theoretical and the experimental equation of state for methane plus trihydrogen sulfide, and the PV contribution favors the assemblages. We also studied the SH bonding by plotting the HS distance as a function of pressure for several phases. Using the R3M as an example, under pressure, SH1 and SH2 bonds are approaching each other, and S3 bonds are decreasing as the phase undergoes the pressure-induced bond equalization. However, due to the fact that the intercalation of methane molecule would break the symmetry, the SH1 and SH2 bonds are slightly different, and both of them are slightly shorter than the SH bond in the trihydrogen sulfide. So when we have more formula units in the primitive cell, we found that varying the orientation of the methane molecules might further stabilize the structure at higher pressures. That's how we find the PNMA structure. So soon after we published this work, another study identified a I-bar43M structure that's very similar to the PNMA phase we found. And these two structures, the enthalpy difference between these two structures is very small, actually within the convergence criteria of the calculation. So we estimated the superconducting properties for these structures, comparing all of these structures are metallic at their stable pressures, and using R3M plots as an example. So the metallicity are mainly due to the trihydrogen sulfides frameworks. The methane molecule barely contributed anything, and there's very obvious hydrogen sulfur characters and the hybridization, and it's very indicative for the hybridization. So for the superconductivity, R3M at 150 GPa has the lambda that's almost twice as big as the CM phase. Also, the lambda for R3M phase is comparable to that was found in the trihydrogen sulfide with high TC. However, because the omega log was a bit smaller in the R3M phase, so does its TC. So for the R3M and PNMA phase, the lambda decrease as pressure increase. And this is not offset by the increase of omega log, and therefore their TC decrease as pressure increase. Because all of these structures have large lambda, we also calculated their Eliashberg TC, and that would be this column. So comparing to the TC we find for PNMA and to the structure of I-bar43M, our Eliashberg TC at 150 GPa is much higher. So as a conclusion, CSH7 is dynamically stable above 100 GPa, and it can be viewed as a distortion of the PM3' perfect symmetry perovskites. And they can be characterized as methane molecule intercalated to form the distorted trihydrogen perovskite frameworks. They are promising conventional superconductors with the highest TC estimated as approaching 200 Kelvin. So recently, Professor Ranga and his team published the experimental measurements for the CSH system at high pressure and found the highest TC to be 287 Kelvin at 265 GPa. So this phase have not been identified yet. We believe that would be a good motivation for a future project. So the last hydride system that I want to talk about today would be lithium fluoride hydride system under pressure. And this manuscript is under preparation, should be coming out soon. So lithium fluoride is a very interesting ionic compound because it has a huge band gap, and it has been used for a wide range of applications. For example, it has been used as pressure standard and pressure transmission medium in the diamond envelope cell, and it has been used as the window material in the dynamic shock and ramp compressions. So it would be very interesting if we can study the pressure-induced reactivity between the lithium fluoride and hydrogen. That's why we started this project. And we are so lucky because the binary systems of lithium hydrides, hydrogen fluoride, and lithium fluoride have been studied under pressure, providing the ground for us to explore the ternary system. So we carried out evolutionary searches on many structures. A full list is listed here. So we identified six structures out of them within 50 millieV per atoms above the hull. There is no thermodynamically stable structure because all of them would finally decompose into lithium fluoride at 0 Kelvin though. So we listed all the metastable structures from the lowest enthalpy 1 to the highest enthalpy 1. There are shared structural motifs that's interesting. For example, there are linear symmetric bifluoride anions in the lithium F2H structure, and it's also found in lithium 3F4H and lithium 2F3H. There are also nonlinear asymmetric bifluoride anions that's found in lithium F2H, lithium F4H4. And the bifluoride anions is very interesting in lithium F3H because it's linear but asymmetric. So there are longer anions for trifluoride, which contains 5 atoms as shown here. And this is also found within this lithium F4H4 structure. And this complicated lithium F4H4 structure also contains the trihydrogen cation. So I want to clear this up a little bit. So the famous bifluoride anion have 2 forms. The linear symmetric form can be viewed as containing 3 center 4 electron bonds, but the nonlinear asymmetric anions can be viewed as FH interacting with F- through strong hydrogen bonding. And in crystal structure, the asymmetric anion is more common. However, due to the fact that, because of the presence of Lewis acid, however, due to the cations are locating at the symmetric positions in several of the phases, the bifluoride anion remained linear symmetric because there's no electrostatic forces. So we also carried out integrated crystal orbital Hamiltonian population analysis on the bifluoride and trifluoride anions. This is the values represents the bond strengths. So in the table, it's we only analyze the bifluoride anions with the 3 atoms. So comparing to the gas phase model of the linear symmetric anion, the anions in the ternary phases under pressure would have a shorter bonds and being stronger. Comparing to the HF bonding in the one-dimensional HF zigzag chain of the HF phase, we find that the HF bonds in the bifluoride anion of the ternary phases would be shorter, but also weaker. That's suggesting that the complicated chemical environment of the ternary phases is destabilizing the anions. So we also took the trifluoride anions out of these 2 phases and analyzed them. As we expected, it is agreeing with the ambient model that the terminal FH bond would be stronger and shorter, and the middle FH bond would be longer and weaker. So it can be viewed as 2 FH interacting with the middle F minus. So we plot the electron localization function as a contour for the 3 selected structures. So there are missing points in the contour because it's really hard to choose a perfect plan that covers everything. But we can still see that there are very high alpha regions around the H3 cations because it's 3-center 2 electron bonds, and there are high alpha regions located around the F atoms, and the alpha around the shorter and stronger FH bond is higher than that of the longer bonds. So 5 out of 6 structures in the 5 out of these 6 structures are non-metallic. And the only one being metallic is lithium F3H. For the non-metallic phases, the band gap are large, ranging from about 10 to 14 eV. This metallic structure at the Fermi level, its metallicity is mainly due to the F2p characters, and it's not caused by the pressure-induced band broadening. Instead, it is based on the pressure-induced dissociation of the F2 molecules. Because it's metallic, we decided to estimate its TC value and calculate their electron phonon coupling parameters, and it's a really bad superconductor. Actually, we cannot call it a superconductor. So the conclusion would be the low-lying ternary lithium fluoride hydrogen system does not have, are not good candidates for the superconductivity. So as a conclusion, we identified 6 metastable structures for a lithium fluoride hydrogen system that's within 500 millieV per atoms above the Hall at 300 GPa, and they would contain the bifluoride or larger trifluoride anions and lithium cations. And the unique trihydrogen cation was found in the lithium F4H4 structure. So for the longer anions, it can range from multi-centered interactions to classic 2-centered 2 electron bonds with an HF hydrogen bond. And we suspect that when N is greater than 2, there could be more metastable or stable phase. Therefore, we carried out a testing search on lithium F4H3, found a metastable structure with about 20 millieV per atoms above the Hall. And lithium F3H is the only metallic phase. So then I will give a quick summary. So we had two projects studying the phosphorus hydrides under pressure, one below 100 GPa, one up to 200 GPa. Both of the phases were, both of the structures found PH₂ to be the good candidate for superconductivity. We found no superconductivity for iron H5 in the iron H system studied under pressure, and we studied two ternary systems, CSH7 and lithium fluoride hydrogen, found a good superconducting candidate, good candidate for the superconductivity as CSH7, and found a unique structural motif in the lithium fluoride hydrogen system. And I would like to thank my advisor, Professor Eva Zurak, my previous current group members, my collaborators, Professor Hamley and Professor Liu, the Center for Computational Research at UB, and NSF, CDAC, Department of Energy for financially supporting our research. And thank you. That would be my talk. And please ask questions.
Thank you very much, Tiang. Beautiful talk.
Thanks.
I really particularly enjoyed your detailed discussion of structure bonding relations in each of those systems.
Yeah.
So I'm sure there are questions. We have people from the West Coast through to Western Europe, many different time zones. So feel free to unmute yourself or use the chat.
Unmute. Good evening. Ross, may I have a question?
Yes, please go ahead, Leonid.
Yeah. So my name is Leonid Dubrovinsky. Very interesting talk, a lot of interesting data. I have one rather technical question. We know that the hydrogen is rather light, and under severe compression, we have to expect, and there were a couple of theoretical work which are confirmed that it have to be anharmonic. Did you consider anharmonism in these materials and in your calculations? Thank you.
Thank you. That's a really good question. Yes, it should be considered, but we don't do that because it's computationally too expensive for us. I'll explain this a little bit. We cannot consider this in the evolutionary searches because in each of the run, it would calculate probably 1,000 of the structures. So that's kind of too expensive to include that. But I do agree that we should consider that for hydrogen. But probably if we can predict a good structure, and then we would do projects to consider the anharmonic effect on that. And probably other groups would do that too.
You have been looking at the effect of rotation effectively when you have molecular hydrogen present. Mm-hmm. Your models for the barrier. So that's important as well.
Yeah.
That's also a kind of quantum effect. I think Roald has a question.
Yes, hi Tiang. It's great to hear this work.
Thank you.
I have a few things, but first let me just clear some things. Mm. On the phosphorus hydrides, if I understand you right, you have not found any phosphorus hydride at any pressure that is thermodynamically stable with respect to the elements.
Yes, you are correct.
Right. So therefore, you calculate metastables.
Yes.
Okay. I wonder if there isn't something waiting there that hasn't yet been found. That's maybe not just phosphorus and hydrogen, but maybe something else in there. A second thing I want to check is on the methane in SH3, which is a great story. What you found was that when you substituted one of the SH3 sublattices by methane, that you got a lower TC. So this is that right? Lower TC than what was observed experimentally in the Diaz experiments.
Really quick. Yes, comparing to the trihydrogen sulfide, it would have a lower TC.
Not only compared to the trihydrogen sulfide, but compared to whatever Diaz and co-workers found.
Yeah, the TC is lower. Yeah.
So you haven't explained the Diaz et al. Results, that maybe there is some other carbon-containing structure. And I know of some preliminary work on just doping carbon instead of sulfur, but your calculations with methane do not explain the high TC.
Yes. So we actually predicted the structure before the experiment, but yeah, I do agree. This phase are different, our structure and the experimental phase, and that's actually trying to find the experimental phase is the current project we are doing.
Okay.
Yeah.
Okay, more questions? Please just unmute yourself.
Yeah, I have a question. It was a very good talk, very interesting, super many structures. One quick one on the iron hydride systems. You looked at, you said several times that iron H8, that there was atomic hydrogen there. I would have guessed that they were hydrides. Did you check? Did you have any reason for saying atomic hydrogen there?
Here, the X motif, am I understanding correctly?
I think it was page, yeah, it was here.
No, I believe we didn't check the chart. Yeah, no, sorry.
Okay.
Yeah.
No, thanks. I can sneak in one more quick question on this the Gaussian smearing, dependence on the TC on the Gaussian smearing. That was pretty dramatic. How many predictions out there do you think are bogus because of this?
I can't tell how many, but yeah, that would be a mistake. That would be a possible mistake to get in the calculations for some systems. Because for honestly, if you would have a large Gaussian broadening out in the output of the calculation for any system, they all become superconducting at some point, as long as they're stable, because the approximation is too bad there. So we normally would just limit the selection at very low Gaussian broadening values to make it correct. But yeah, there would be mistakes.
I also want to point out that Lilia Boeri showed something exactly the same for the FEH5 structure, and her study and our study were published like very similar times.
Thank you.
Thanks. More questions?
Hi, I have a question. Here, let me start my video. Hi, thank you for the talk, by the way.
Thank you.
I was wondering if you had done any more analysis on why the predicted TC of the lithium fluoride hydrogen ternaries was so bad?
No, so we didn't focus on that part because most of the structures were non-metallic and we were not expecting that. But I would have a guess on that. So first, we are not, this project was not really focusing on like the system with a lot of hydrogen. So the stoichiometries that we studied would have lower hydrogen content compared to others. That might be a reason, I think.
Yeah, that would make sense.
Mm-hmm.
It's just kind of fascinating, the idea of turning lithium fluoride, which is like the best insulator with the largest band gap into a superconductor. Yeah.
Yeah.
Anyway, thank you.
Thank you.
Thanks. More questions?
I had a question, it's Roald again, on back to the phosphorus. So some of those PH₂ structures came from layers of elemental phosphorus and layers of hydrogen. And that's a natural starting point, since that is thermodynamically, the elements are thermodynamically more stable than PH₂.
Mhm.
So when you optimize the structures, some of the H2 decomposed and bonded to the hydrogen.
Yes.
But the phosphorus retained pretty much the simple cubic structure that elemental phosphorus has that I know about at 50 GPa, and presumably it's there at 80 GPa. Now for the next set of ones, the ones at the higher pressure, what is the elemental phosphorus structure at the higher pressures with which you start out?
I believe it would be simple hexagonal phosphorus. Yeah.
So that is the favorite structure of elemental phosphorus at 200 GPa, let's say. Mm-hmm.
Yes.
Yeah. I think this is a very fruitful direction to go, to start from from interfaces, thin interfaces of the elements, in order to see the structures. It's also something that conceivably I can imagine could be done experimentally. That is, in fact, one can use nanofabrication to form thin films of different kinds of elements and then compress them. So there is something very interesting about the approach that you're using here.
Yeah.
Yeah, related to that, the connection to phase 4, hydrogen, is very interesting because that's a 2D material.
Oh, yeah.
Very
that's true.
I like that parallel.
Yeah.
And that's a high temperature phase 4. And so that leads me to ask, to what extent can you extend some of these calculations to high temperatures where you look at structural transitions induced by temperature and then the associated electronic properties? You haven't really done that yet, right?
Yeah.
Okay, more questions?
Hi, Kianga. This is Tanmo. Nice talk.
Thank you.
I had some question about the PH₄ study. Mostly, like you use the Nernst elastic band to prove the rotor motion of the hydrogen. I thought it was really interesting. Could you kind of briefly again go through like the steps you took to prove that? I just wanted to understand because I maybe missed some parts to that.
Oh, so you mean this page, right?
Right, yes.
So what we did is we start one connection by connecting the C2M and the C�MM phase, and the intermediates are just rotating, like slightly tilting these H2 molecules to get to each other. And then we would calculate the barrier, which is the structure that with the highest enthalpy there. And we also did the same way, but rotating different layers for C2M. We did 3 runs. First is rotating all of them, like at the same time. And then rotating only the top and bottom layers. And another run is rotating the middle layers, just to see how this would affect the barrier calculated.
I see.
Yeah.
Okay, that makes sense. Thank you.
Thank you.
Okay, if there are no more questions, thank you, Tianga, for a beautiful talk.
Thank you.
And thank you all for joining us. And we'll see you in the new year. We're all hoping 2021 is better than 2020. Bye-bye.
Bye.
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 Bye. Thank you.
Bye. Thanks.
Thank you.